Okay, so today what I want to do is I want to look at the 2019 Rocky Mountain Regional Contest. So this is the region that we are in, and this is the contest, I guess, a year and a half ago, but technically we are still the one that's happening this year is actually the 2020 Rocky Mountain Contest because we are delayed. So this is the last one, basically. And what I want to talk about are the problems that are solved, the five problems that are solved the most often. So there's piece of cake A, fantasy draft, integer division, dietary, and lost lineup. Those are the five. And if I have some time, maybe I'll talk about H. Um, what I want to say, I guess, is when we start to look at these, is that the five problems, whether you call them easy or medium problems, don't really require any special knowledge in terms of algorithms. It's not, you don't really have to know anything from, let's say, 3620 or advanced classes in order to be able to solve these problems. And I mean, you do need to know a little bit, let's say, from 2620, but they are certainly approachable even if you don't know too much in terms of advanced ideas. So what I want to do is I want to show you how to do some of these problems. I want to show you how to do them quickly and of course accurately. And if you look at the standings, so this is last year's contest. We were fifth with 8 problems solved. So of course, if you only solve the 5 easy problems, so which are these 5 problems, A, B, D, um, I, and what, K, you would be anywhere from 12 all the way to 28. And out of what? Out of 72. So if you solve 5 problems, regardless of how quick you are, you would be in the about top third of the contest, right? Because there's 72 teams, 73 teams. So a third of it is about 24 teams, and you are kind of right about here if you solve 5 problems. If you solve them 5 problems quickly and accurately, then you could be as high as 12 spots, right? And you see our second team from Lethbridge, where are they? Here they are. This is our second team. And they solved 5 problems, but some of the problems they took a little bit more time and also incorrect submission. So these two, that means that um, they have submitted one wrong and one right. That's why there are 2 attempts. And this one down here, they actually submitted 3 times. That means they have 2 incorrect submissions before. So basically, they have 4 incorrect submissions. There's 1 incorrect submission for C, but they never solved C, so it doesn't count. So they had 4 incorrect submissions. That's 80 minutes. So if you subtract 80 minutes, that would put them up a few spots, right? But anyway, let's look at some of these problems, and you see some teams, even our team that at 26, the first problem they solve in 9 minutes, right? And then they solve in 23 minutes, so that's about 14 minutes. And then these are a little bit harder to say because they might have submitted a long time ago, but then it took them a while to fix it. So, and you see the top performers, they solve them pretty quickly as well. 10 minutes, 8 minutes, 51, 58, 83. Okay, so what I want to do is I want to just show you these problems one at a time. And if you are new to this contest, make sure that you look at the scoreboard because after a few minutes, after 2 minutes, somebody already solved the problem. After 5 minutes, this problem has been solved. And if you haven't even read, right, so actually after 9 minutes, the U of A team already solved 3 problems, A, D, and K. Now, why can they solve so quickly? Because these are 3 people together, right? And maybe while this person is typing, the other person was already working on it on paper or something like that. So it's not exactly that it took them exactly 3 minutes, but anyway, it's pretty fast. And in 10 minutes, after 10 minutes, even if you haven't solved anything, you look at the scoreboard, you'll see a bunch of people solving A already, You see some people solving D and K. So if you're not looking at those problems already, you know you should be. Okay. And for example, let's say for some reason you started looking at F and you really like F and you started working on it and working on it. And you see the only submission that's correct for this problem, it's at 4.5 hours. So after an hour, you see that nobody has touched it, or maybe you see that somebody has submitted it wrong many times. Oh, actually, there's another solution. Then you know that you should probably give up unless you have some great insight. But if you're starting out, it's unlikely that you have some great insight that the top teams don't have. Okay. On the other hand, I thought that F was really easy, but that's me. Okay, anyway, piece of cake, problem A. Okay, so let's read the problem. It says it's Greg's birthday. To celebrate, his friend Sam invites Greg and 2 other friends for a small party. Of course, every birthday party must have cake. Now, when I say read the problem, I'm reading it word by word, okay? You want to make sure that you read everything and make sure that you identify anything that's important. Don't miss anything. So Sam ordered a square cake. So immediately the word square, you have to be a bit careful. You have to remember that. She makes a single horizontal cut and a single vertical cut. In her excitement to eat cake, Sam forgot to make these cuts through the middle of the cake. Of course, the biggest piece should go to Greg since it is his birthday. Helps Sam determine the volume of the biggest piece of cake that resulted from these 2 cuts. Okay, so there's a picture here. So this is a square cake. The input consists of single line with 3 integers, and n is an integer from 2 to 1 to 10,000. The length of the sides of the square cake in centimeters. Okay, so the whole length, it's n, and it's both length and width because this is a square. Then h is the distance of the horizontal cut from the top edge of the cake in the centimeters. So they draw a picture. Okay, so this is h, and then you cut here. And then this is v. V is the distance of the vertical cut from the left edge of the cake in centimeters. So this is V. Okay. And then this is illustrated in figure above. And then finally, they talk about the volume. So the problem with volume is you need 3 dimensions. And it turns out that the 3rd dimension is 4 centimeters. So what basically you can pretend that this is a square, and then calculate the biggest area of these 4 pieces, right? And then whatever answer that is, you multiply by 4. Okay, now what else do they ask? What is the output? Display the volume in cubic centimeters of the largest of the 4 pieces of cake after the horizontal and vertical cuts are made. Okay, so basically you have 4 pieces of cake and you need to figure out which one is the biggest. That's the question. Okay, so, you know, as I said, what you can do is just take the volume, take the area of the rectangle, this rectangle here, and just multiply by 4. So what is the area of this rectangle? Well, it's very simple, right? It's h times v. That's one possible answer. What about this one? Well, if the whole thing is n, and this is v, so then this must be n minus v. So this rectangle is going to be h times n minus v. This part, for the similar reason, is n minus h. So this is going to be n minus h times v. And then this one is going to be n minus h times n minus v. Right? So these are the 4 pieces. And so if you want, what you can do is you can just compute, you know, I don't know, int a1 is equals to h times v, a2 is equals to h times n minus v. Okay, I put some semicolons. A3 is equals to h times, wait, n minus h, I mean, n minus h times v, and then A4 is then n minus h times n minus v. And then the answer is just the max of A1. Now, you want to basically pick the maximum of all of them, but in C++, max will only allow you to take max of two things. So you're going to have to do it a little bit differently. So you're going to have to do it sort of two at a time. And maybe I do it like this. Max A answer A3. And if you want, you can even do it in an array or something. That doesn't really matter. And then you output at the end, Cout answer times 4. Okay. And of course, max is a STL function. And if you were to include algorithm, it will include max and a whole pile of other things. Okay. If you're one of those people like me that tries to optimize things in terms of includes, so you can do pound include bits slash std c++.h, and that basically includes everything that you can possibly include in C++. And this is definitely not recommended in normal real life. You don't want to include everything that you possibly can include because you can introduce all sorts of conflicts if you're not careful. But more importantly, this is non-standard. This is a G++ feature that is not necessarily a C++ standard feature that exists across all compilers. But for competitive programming, you can squeeze every single bit of advantage that you can because we don't care about code quality in those senses. Okay, so you can do this, or you can just include what you need. Of course, you have to include IO stream if you need to do IO, which of course you always do. And then you read in H and you read in N, H, and V, and then the computation is just this. Are there any questions? Now there's a shortcut. If you look at these formulas, it's always going to be a height times a width. And the question is, do you take h or n minus h, or do you take v and n minus v? Instead of computing all these four and then computing the maximum, in fact, there's a shorter way of doing this. You can actually just take the maximum of v and n minus v, multiply that with the maximum of h and n minus h. Because if whichever one is bigger in the h, n minus h, you want to take that part. Similarly, whichever part is bigger from the vertical side, you want to take that part, and that will give you the largest area. So you can actually just do this, take the max of each dimension and then multiply together. That's equivalent, and it's shorter. The final thing that you have to ask a little bit, or you always should ask, is what should your variables v, n, and h, and also answer be declared to be? Like what data type, right? You might by default write the word int like this, and then you always have to ask, you should always ask, is this big enough? So int in C++ is 32 bits. So signed integers means that the max is 2 to the 31 minus 1, which is approximately 2.147 billion. And they tell you that n is at most 10,000, h and v are at most n minus 1. So this is well within range of the 2.147 billion. But what about answer? Answer is two of these numbers multiplied together. So this is definitely less than 2 to the 15. So it's kind of good to have some idea of how big things are. 2 to the 15 is about 32,000. Okay. So if I take two of these numbers and multiply them together, answer is at most 2 to the 30, which is still okay. Okay, so a rule of thumb is that if you try to multiply numbers and they're about 32,000 or so, then you're safe. If you're bigger, then you start to have to be very careful. And if let's say this is, I don't know, 60,000, then you might be in trouble. Okay, so if this is 60,000, then you can't just use int, and then you're going to have to use the 64-bit integers, which in G++ is long, or you can also use int 64t, I believe. I just use long. Both of these are 64-bit integers, and that would be okay, but you have to be careful also that you don't write something like this. Okay, so what don't you want to write? If we write, let's say int v and h and n, and you read in v, h, and n, of course, and then you write long answer equals to v times h. And let's say v and h are both 60,000. Well, if you do that, this will actually overflow, even though the answer can store in the 64-bit integers, because on the right-hand side, both of these are integer values. And when C++ sees that you're trying to do a computation with integers, it will do the computations in 64-bit, in 32-bit integers, which will overflow. And then the result that has been overflew already, then goes in. So you would already get the wrong answer. So the easiest way to avoid that is to just declare everything to be long to begin with. And then you're not going to have any problems. Okay. Okay, so I'm taking a really simple problem and telling you a lot of details. Why am I doing this? Because I want to make sure that if you have a problem that's actually easy, you see all the different parts to make sure that it is actually easy, that you don't miss any details, that you just do it quickly. Okay. A lot of these things that I talk about, watch out for this, watch out for that. If you do a lot of these problems at practice, and maybe if you are not too careful and you get stung a few times, you will remember them. It just becomes sort of second nature, and you just instinctively look at all of these things, right? But if you're starting out, then I just want to point out these are all the things that you should be looking at. Okay, are there any questions? Okay. All right then. Let's look at the next problem. So if I look at this problem, so the deep green problems are the ones that basically are the first submission for that problem. So the first submission for A was in 2 minutes. Somebody solved in 2 minutes. And then K in 4 minutes, somebody solved K. And then in 5 minutes, somebody solved D. So clearly A, D, and K are not that hard. Okay. The other two took a little bit longer. So B, for example, the first correct submission was 38 minutes. And then I, which is the other one I want to talk about, the first correct submission takes 19 minutes. Yeah, I don't know what happened to these guys here. They took 4 tries to solve B. Anyway, That should be embarrassing. Anyway, so let's look at the next problem, which is K. K is the one that is that the one that's solved next? 4 minutes. That's right. K was solved in 4 minutes. Okay. Now, even though it was solved in 4 minutes, it doesn't mean that it was the same team that solved A first, right? Because everybody can choose whichever problems they start looking at. And I think for the less experienced teams, it doesn't hurt to that everybody start reading once you identify what the easy problems are, that everybody start reading it, and maybe have two people try to work on it at the same time. Making sure in the normal times, I would say maybe one person look over the other shoulder to make sure that everything is done right. But I'm not completely sure how we're going to achieve that now. But maybe at least you have some way to share your files so the other person can check. And if you have more eyes, usually means that you'll catch mistakes easier. Okay. Oh, the other thing that I suppose the other thing that you should always look at is for each problem, there's a CPU time limit, and you should make sure that the algorithm that you use is not going to be too slow. But of course, the cake problem, there is no real algorithm. It's just one single multiplication of two things. So it doesn't really matter what you do. It's going to be fast. Okay, lost line up. This one might be a little bit. This one, there's 1 second. So let's see. Let's read this. Okay. It says, Jimmy and his friends were all standing in a lineup for ice cream when a huge gust blew them all around. So this is definitely a Lethbridge ice cream shop. The friends want to keep things fair and make sure everyone gets their ice cream in the order they started with. The friends do not remember the order, but each of them remember exactly how many people were between them and Jimmy. Jimmy is always the first person in line. Can you help him and his friends remember the order? Okay. Then it says that the input, the first line contains a single integer n, which is the number of people on the line, no more than 100. At least one, no more than 100. The second line contains n minus 1 space separated integers, where di is the number of people between the I plus 1 person and Jimmy. Why is it I plus 1? Because Jimmy is always the first one. Okay, so Jimmy is always first. Print a single line with n integers, the people in the order of the original lineup. It is guaranteed that there is always a solution. Okay, so this is definitely a little bit more challenging than the cake one, and it's usually a good idea to work out the sample input and output, especially when it's small like this, to make sure that you actually understand the problem. So let's just make sure we understand the problem. So you have two people here. Jimmy is always the first one. So Jimmy is always the first one. And then the second person, this one, there's no one between that person and Jimmy. Well, if there are two people, they have to sit next to each other. There's no one in between, right? So that's the answer. Okay, that's not very exciting. So let's look at the second input. Okay, so Jimmy, it's again always the first person. And now this time there are 4 people. Okay, so we don't know where the 4 people are, so we'll just put blanks here. So person number 2, because this person is actually not person number 2, where is he? There's one person between him and Jimmy. So if Jimmy is here and there's one person here, then the second person must be here. The third person says that this third person must have 2 people between him and Jimmy. So here, 2 spots behind. And then finally, 0 spot behind, it's the third person, it's the fourth person, and that's the answer. Okay, so that's the idea. So you see, if you have n people in general, okay, it doesn't matter. So this is person 1. Jimmy is always here, person 1. And we'll just use an array, put it in an index 0 to n minus 1. Okay. And if I look at these numbers, if I have 4 people, it's that these people are always represented by 2, 3, 4, and if there are more, 5, 6, 7, 8, 9, and so on. Okay, so if there are 10 people, then there'll be 10 numbers in this order. This number says how many people are between Jimmy and that person. Well, if you look at this, let's say at position 3, if you're looking at this position, how many people are between Jimmy and position 3? Well, it's 2, right? And if you're in position 4, how many people are between Jimmy and position 4? 3. And it doesn't take you too long, I hope, to realize that the number for any particular position, call it P, the number of people between Jimmy and that position is always P minus 1. Or you can run it backwards. If you know that there are 3 people between you and Jimmy, then the position that you should be in must be 4. Okay, so if you know, going another way, if you know that you have a certain number, call it the gap, G, if you know that there are G people between you and Jimmy, then you must be in position G plus 1. And that's pretty much the only thing you have to do. Okay, so what do we mean by that? I know I can do a counter, and I know that these are 2, 3, and 4. So for person 2, the gap is 1. 1 plus 1 is 2, so I put 2 here. For person 3, the gap is 2. 2 plus 1 is 3, so I put 3 here. 0 plus 1 is 1, and that's the answer. So how do I write this code? Before I go on, are there any questions about how this works? How do I write this code? And then is this algorithm okay? Is this algorithm fast enough? Well, this algorithm, basically for each one of these numbers, I do exactly one calculation to figure out where to put that person. So it's linear time. Linear time for something that's up to 100 people, it's nothing. So how do I do this? Okay, so I'm just going to pretend that you already have main. This is all in main. So I'm going to have an array int. Okay, why don't I just write int main? Hang on, let me write it up top. Okay, int main. Return 0. So what do I have? I need and I'll read in and I'm going to have an array that store the answer. So int a, and I can store the answer up to 100 because I know that it's at most 100. And I'm even going to just initialize it like this. This will make sure that the array, so 0, 1, 2, up to 99, the first element is 1, and any unspecified elements are automatically filled with zeros. In our case, it actually doesn't matter what the unspecified elements are, but that's what happens when you try to initialize an array and you don't specify enough elements. The rest are initialized to be 0. Okay, so now I can say for int I equals to 2, I less than or equal to n, I plus plus, because these are all the people that I have to place. So I'll have a gap size. I'll read in the gap. And now I would say a bracket gap plus 1, it's equals to I. Okay, so gap plus 1 tells me, so if I have the gap is 1, it tells me that I should put in position 2. What should I put in position 2? The index of the person. And run this loop through, and I would have all of the numbers filled. And then all I have to do is I just have to print the array out. And don't forget to put a space. So this is space. It is okay in Caddis to print one more space at the end, right? So here I'm putting a space after every single item. So if I'm printing 1, 2, 3, 4, there will be a space after every number, and then there'll be a new line. Okay, extra spaces are acceptable in Caddis, but if you forget about a space and you print 23, that's wrong. Okay, so you have to make sure you have at least one space here. And that's pretty much it, right? And this is, of course, big O of big theta, doesn't really matter. And time, linear time, because each of these loops basically runs at most n times. And you cannot do any better because just reading the input would be linear time. So, and writing the output has to be linear time, so you can't actually do any better. Does that make sense?
Yeah, I think it makes sense.
Okay. So those are the first two problems, and you see why some teams can solve it in 2 minutes and 4 minutes and so on. I mean, I took quite a bit of time to explain this, but for the really experienced people, they just look at it and just do it without really throwing everything out. But again, you know, when you're starting out, don't try to be the one that solve a problem in 2 minutes. It's okay if you solve it in 20 minutes or even half an hour, as long as you're steady, right, and then do it right. It's better that way than to do it wrong and get a 20-minute penalty each time you do it wrong. Okay, so let me clear the screen here. Now let's look at which one? D. D is the next one. Now D is actually not. Actually, let me look at this again. If I look at the number of people solving these problems, okay, so A, 71 teams solved it. Remember, there's only 73 teams that came, so almost everybody that showed up got A. K, again, almost everybody, just maybe a couple of teams that didn't get it. But then there's a bit of a drop between D and I. So they are still the next level of problems, I guess you can call it, but they're not as easy as the previous one. So let's look at D and I. I don't know which one to look at first. They're all kind of similar. So D is this one. Okay, integer division. So what does it say? In C++, division with positive integers always round down. Because of this, sometimes when two integers are divided by the same divisor, they become equal even though they were originally not equal. For example, in C++, 5/4 and 7/4 are both equal to 1, even though 5 and 7 are not the same. Given a list of non-negative integers and a divisor, how many pairs of distinct entries in the list are there that give the results when they give the same results when both are divided by the divisor in C++? Okay, so you have a bunch of numbers, you're dividing by some divisor, how many of them will have the same, how many of them pairs of distinct entries? Okay, first line contains two integers and there are up to 200,000, at least one, which are the number of elements in the list, and then some divisor d, which is anywhere from 1 to 10 to the 9. 10 to the 9 is a number that you should remember because 10 to the 9 is a billion, and a billion is basically the largest power of 10 that can fit inside a 32-bit integers. So basically, a normal integer would be good enough. The second line of input contains n integers, a1 up to an. Each number is from 0 to 10 to the 9, where a bracket I is the ith element of the list. Display a single integer indicating the number of distinct pairs of indices I and j, with I and j being between 1 and n, I is less than j, such that when you divide the ai by d and aj by d, the results are the same using C++ integer division. Note that the numbers in the list are not necessarily distinct. So you're looking for distinct indices, but not necessarily distinct numbers. So what does that mean? So for example, if I have something like 1, 1, 2, 2, and I'm dividing by 4, then all of them, when I divide by 4, goes to 0. So this pair, this pair, this pair, this pair, all 6 pairs. Okay, all 6 pairs are, when you divide by 4, goes to 0, so the answer is 6. Okay, so you're looking for all possible pairs of entries, even though some of the pairs are the same. So this pair, for example, is 1, 2. This pair is also 1, 2, but you count them separately. They're different pairs. So this is the first problem where you have to be a little bit careful in terms of algorithms. But again, before we start, we need to actually look at the sample input to make sure that we understand what's going on. Okay, so it says that there are 5 numbers we're dividing by 4. So 4, 5, 6, 7, 8. And when I divide by 4, 4 divided by 4 is 1. So divide by 4. 5 divided by 4 is 1. 6 divided by 4 is 1. 7 divided by 4 is 1. 8 divided by 4 is 2. So which pairs gives you the same answer? Well, this pair, and this pair, this pair, and this pair, and also this pair. So there's 6 of them. 1, 2, 3, 4, 5, 6. And then no other pairs of 1s. And of course, this 2 cannot be the same as anything. Okay, the next one, you divide by 1. Okay, divide by 1. None of them are the same. Right, so it's 0. That's easy. Okay, what about this one? 6 divided by 1. So sorry, 6 numbers divided by 1. So of course, when you divide by 1, nothing happens. And you want to know how many pairs have the same divisor. Well, have the same quotient. This pair, and this pair, these are the 1s, and the 2s, this pair, and this pair. Okay, so again, there's 6. So that's the that's how this works. Are there any questions about how you get these answers at all? Okay, maybe it's not clear how you get it, but like how you compute this for bigger case, but at least this is how the sample input works. And then you look at this, and the CPU time limit is 2 seconds now instead of 1. So obviously something a little bit more is going on because they give you 1 extra second compared to the other ones. Okay, so what can we do? Can we get an answer at all? Any, doesn't matter how long it takes. And it's actually really easy if you just want an answer. So what? So imagine that you already read it in. So you have int a up to 200,000 and int n, and you already read everything. Okay, so you already read inputs. I assume you know how to read inputs. So now what? I can say int answer. So this is the number of pairs that I care about, would be 0, and then I'm just going to count. Okay, so for int I equal to 0, I less than n, I plus plus. So I try all possible i's, and then j has to be greater than I. So I start j to be 1 bigger than I, j less than n, j plus plus. So why does it have to be greater than I? Because the answer, the problem says find all pairs such that I like satisfy this. Now I'm using in my array in C++, I'm using 0 base, so that's why I start at 0 and end at n minus 1. But the problem statement is from 1 to n, so that's why there's a slight inconsistency, but that's the only thing. And then you just say if AI divided by B, oh, there's a B too, I forgot about B. If AI divided by B is the same thing as AJ divided by B, then answer plus plus. So every time I found a pair, I just increment it. I see out answer, and that's my answer. That's my code with you know the usual headers and all that other stuff. So this just basically goes through all possible pairs and counts. Right? Every time I find a pair, I just count, and then I get an answer. Is this a good idea? How long do you think this piece of code will take? Long, okay? But how long? So this is a typical big O of n square loop, right? So the first iteration when I is 0, j basically goes from 1 to n minus 1. So the first iteration, the inner loop goes n minus 1 step. Then the second iteration, when I goes to 1, this goes from 2 to n minus 1, so it's n minus 2 steps. And then the third iteration is n minus 3, and so on, and eventually go down to 4, 3, 2, 1. And when you add it up, this is a classic n times n minus 1 over 2, which of course is the big O of n squared. And n, remember n is 200,000. So n squared is a lot, right? So 200,000 is 2 times 10 to the 5. So n is this. So n squared, it's going to be 4 times 10 to the 10. So what is that? That's 40 billion. So is that big? Is that small? What is big and what is small? So when usually the rule of thumb in programming contests, when you have, let's say, a few seconds, if they give you a few 1 or 2 seconds, let's say 1 to 3 seconds, if you do this rough complexity analysis, right? So theta of n squared plug n in is 40 billion. Anything less than or equal to 10 to the 6th, well, 10 to the 7th. So 10 to the 7 is 10 million. Anything that's less than or equal to 10 million, don't sweat it. It's going to be done before you can even blink. Okay, 10 million, it's not much. 100 million, so let me put, let's say 10 million to 50 million, it's probably okay, depending on whether you're at the 1 second end or the 3 second end. But when you get to 100 million, so 10 to the 8, you have to be really careful. You have to have really optimized code, and probably it's not going to be enough. And anything bigger than 10 to the 8, you can forget it. Okay, so anything that is about the order of tens of millions, it's probably okay. Now, here's something that you can do if you're not sure. So Caddis is available. You can try it. You can go and try it. You can just, for whatever problem that you just pick a random problem that'll tell you time limit is 1 second. You can just submit something like this, even if it doesn't solve the problem, doesn't matter. And just don't even bother reading the input. Run a double loop like this and try different value of n. And either you're going to get wrong answer because you're not even computing what they're asking you, or it's going to get time limit exceeded. And then you can kind of guess from Caddis for what value of n is it okay to run an n square loop, right? And that might help you. But usually I don't even bother with this because this rule of thumb is usually good enough. So anything about tens of millions, it's okay. If you get 50 million, it's probably okay if you're given a few seconds. And then more, you're really pushing it. So anyway, the point is you're pushing it. This is impossible if you use this algorithm. No way. You're not even pushing it. You're blowing it out, completely blowing out the water. So this is no good. But even if you don't care about runtime, this code is wrong. There is an error in this code. Can anybody see where the error is? Okay, I'll give you a hint. If n is 200,000, and if the array that they give you, is all the same number, let's say they all give you 4, 4, 4. Okay, they're all the same number. How many pairs will have the same divisor? Can anybody tell me? Okay, maybe make it simpler. Let's just say that you have 4 numbers. Okay, you have 4 numbers, they're all the same. How many pairs are there? Well, you can count, I suppose. 1, 2, 3, 4, 5, 6. What about you? What if you have 5? Okay, what if you have 5? How many pairs are there? Well, I guess you can count again. You can get 1 more, you can get 1 more here, then you can get 1 more here, and you can get 1 more. If you count this right, I know that I'm kind of doing it quickly, there should be 10 pairs. But in general, if you have n objects, if you have n items in the list, how many pairs can you get? There are n choose 2 pairs, because the number of ways you can pick 2 things out of n things, that's the number of pairs, which of course is n times n minus 1 over 2. Why do I bring this up? Because if n is 200,000, remember I said that when you have n, you have 2 numbers multiplied together, and these numbers are about 10,000 or so, or maybe about 30,000 or so, then it will not overflow an integer. But if here n is way bigger than 30,000, so this actually will not work because my answer is actually going to overflow and wrap around to give me negative numbers at some point. So to do this right, even if you don't worry about time, this has to be a 64-bit integer. Okay, so that's why I said always think about what data type you use, not just the input. The input is fine, and it's 200,000. You can fit it. You can fit it in here. D is 10 to the 9. You can fit it in an int, but the answer cannot be fit into an int because the answer in the worst case can be 200,000 times 200,000 minus 1 divided by 2, and that's way too big. Okay, so that's a trap that you have to think about. Okay, so now we have a solution that will give us the correct answer even if it takes forever. So how are we going to fix this? Okay, so I'm giving you a clue here. The clue is that if you manage to find numbers that are the same, you don't actually need to find all the different pairs. You just need to know that there are five fours here, and then you can use this formula to say that there are 10 pairs, right? 5 times 4 over 2, it's 10. So let's try again. Let's say D is, I don't know, 4, and then A is, you have different numbers. Okay, like this. What you do is you say, let's say you divide by 4. So if you divide by 4 for everything, this becomes 1. This becomes 0, 0, 0, 2, 1, 1. And then you just say, okay, how many, you have zeros, you have 3 of them. So the number of pairs that arise from 0 is 3. You have 3 ones. So again, 3 choose 2 is another 3. Well, when you have only 1, 2, that doesn't do anything. So then it's just this, and the answer is 6. What if you have a little bit more items? So maybe you have some more like another 7 and maybe a 4 here. Then you have 2 more ones. So this time for the zeros, there will still be 3 more. So for zeros, it'll still be 3 zeros, choose 2, which is 6, which is 3. And then ones would be 5 of them, because there are 5 ones. 5 choose 2, which is 10. And the answer is just 13. Okay, again, you don't have to worry about the 2 because there's only one of them. So what am I saying? What am I saying is that you only have to basically count the frequencies of the different things that you see. You see 3 zeros, you see 5 ones, you see 1 2s, and maybe you see other things. Maybe you see a bunch of 3s, 7 3s, and maybe you see, I don't know, only no 4s, and maybe you see 2 5s. Let's say that. Then all you have to do is take each of these frequencies and compute that number, choose 2. Seven choose 2 is, what is 7 choose 2? 21. 0 choose 2 is just 0. And then 2 choose 2 is just 1. Remember that n choose 2, it's n times n minus 1 over 2. So it's relatively simple to compute. And if you can fill this frequency table quickly, then it's just a matter of computing this binomial coefficients and adding them together. Does that make sense?
Yeah, it makes sense.
Okay, so now the next question is how do you fill these frequencies quickly? And this is where maybe, well, there are different ways, but this is where whether you know C++ and in particular the standard template library, if you know it well, you'll do it in 2 seconds. If you don't know it well, then maybe You need to know that these things exist, and then you have to learn how to do it. So how do I do it? I'm going to use a map. In C++, a map allows you to associate two things. Allows you to associate what's called a key and a value. And you can kind of oh, sorry, I already screwed up, you see. This should be long. So what I'm going to do is I'm going to collect, oh, frequency, I don't need long, actually, sorry. Because counting the number of items is at most 200,000, so the count can never be more than 200,000. I want to basically build this frequency table. So the key would be the actual value, value when you divide by d, and then the value will be the frequency. So the value will be over here. Okay, so what do I do? For int I equal to 0, I less than n, I plus plus. And all I'm going to do is I'm going to say frequency, the table, bracket AI over D, plus plus. That is all I'm doing. That is all I need. So AI divided by D, of course, will take the number that you have here and then divide by the divisor to give you this quotient. And then I'm going to say that for that quotient, remember the frequency to be one more than whatever it was before. So if you've never used map before, map allows you to basically index things by, in this case, a key, which is an integer. So this is my key. And if there was no end, if you have never talked about in this table an entry with this key before, it creates a new entry with the value, with the default value, which for integers is 0. So if you have never seen this entry before, you'll create an entry with the frequency 0, but then when you do plus plus, of course, it increments this and change it to 1. And then the next time you hit this entry again, it will not create a new one. It will just take whatever value you had before and increment it. So next time you see 1, you'll do 2. You see it again, it'll be 3. In other words, it's just a way to count the frequencies of everything. Okay? So this loop will build your table, your frequency table like this. I don't know, 5, 7, 0. Well, 0 will never happen because if you have no 2s, for example, then you simply won't have this entry. Maybe you have a 7, and maybe you have something like this. Okay, so maybe you have 4 entries. Okay, now the next thing that you have to do is to go through these entries and then look at these numbers and compute entries too. So what am I going to do? Where am I going to write this? Maybe I need to write it over here. So let me write it over here. So now we're going to go through the entries in a map. So in C++, there's this range-based for loop that basically this will just go through all the entries in the for loop in the map here. But what are these entries? Well, I'm using auto because I'm too lazy to write out what data type it is, and this will be good enough. But you have to know because each entry consists of, it's a pair of 2 things. The first part is the key, and the second part is the value. In our case, we don't even care about what the key is. We only care about the value. So you can say something like this, int, I don't know. Well, actually, I'm going to use long here. I'll tell you why soon. Long, f is equals to p dot second. So that's my frequency. And then, okay, so before I get into this loop, I actually have to have long answer equal to 0. And then I can say answer plus equals f times f minus 1 over 2. So that's just taking these numbers here and then dumping in the formula for n choose 2. I guess I don't even need so many lines here. Okay, so this actually goes through my array, my map, look at all the frequencies in this column in the values. So this is p dot second, and then compute, this is the binomial coefficient f choose 2, and then just accumulate it in my answer. And then at the end, I just print the answer, and then that's the end of that. Okay. So this one, I mean, the amount of code that you have to write is very small, but there is definitely a lot more going on in here than the first two problems, right? There are other ways you can do it without actually using a map. For example, if you just replace the array by this, right? So you just take every element and divide by the divisor, you'll get this array. If you didn't know a map, you can sort them. So if you sort the array, if you sort A and A plus N like this, so after you have already divided by the D, then you end up with something like this, 0, 0, 0, 1, 1, 1, 1, 1, 2. And then you can scan the array looking for chunks that are the same, right? So you see this many, you see this many, and so on. And then again, once you know the chunks number of things that are the same, then you can plug in this formula. Okay. Now you might ask, okay, is this going to work if f is 1? Because I could have something that only occurs one time, right? And I want to make sure that this returns 0. And if I plug in 1 here, 1 times 1 minus 1, that will give me the 0. So even if you plug in 1, it's going to work. You don't need a special case to make sure that f is not 1. So anyway, if you didn't like the map, if you didn't know you have a map or don't know how to use it, you can sort the array, okay? And sort in C++, remember, don't write your own sorting algorithm, just call sort. Again, it's in include algorithm. And then all the things that are the same will be together. And then you can, if you want, just write a loop that basically is scan for how long each chunk is, okay? You do have to be a little bit careful to make sure that this scan is done in linear time. You don't keep rescanning the same part over and over again, but it shouldn't be too bad. Okay, any questions about this one? Okay, so then let's look at this the next one. This one, Tired Terry. So again, let's look at the CPU time limit is 1 second. So it seems like maybe it's not that bad. So let's see what the problem says. Okay, Terry is feeling tired and he suspects it is because of a lack of sleep. He created a device that records a sleeping pattern over a period of time measured in seconds. Okay, assuming that the recorded sleeping pattern keeps repeating. Okay, so this is a little bit, you have to remember it, assuming that it keeps repeating. Okay, then what? Help Terry by letting him know how often he's tired during each of the repeating time periods. Okay, what does it mean to be tired? More precisely, for integers p and d, we say that Terry is tired at second I if from second I minus p plus 1 to second I inclusive, he has slept for less than d seconds. Okay, so now you have this sort of mathematical statement, and if you're not used to reading this, then maybe it's a little bit tricky to figure out what the hell does it mean. Okay, so what the hell does it mean? That's the question. And if you don't know, if this is kind of complicated, that's okay. What we do is we try to make small example. And the best way to make a small example is to maybe give some numbers. So maybe P, it's, I don't know, let's say 3. Well, okay, let's make it a little bit bigger actually. Let's say P is maybe 5 and B is like 2. Okay, so just to give it some concrete value. And then I'm looking at second, 1, I'm just going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the seconds. Maybe you have more, it doesn't really matter. And if I want to know if I'm tired at second 9, okay, so I would be 9. So we say that Terry is tired at second 9, if from second I minus P plus 1 to second I, he has slept for less than D seconds. Okay, so let's plug everything in. Then we can try to figure out what that really means. So I is 9. So I minus P plus 1, it's 9 minus 5 plus 1. So if you work it out, that would give you 5. So if during these time, you have slept for less than 2 seconds. So basically, you have a record in these 5 previous seconds, and you have to count how many of these 5 seconds you're asleep, and if it's less than D, you know you're tired. Okay, so this P actually says that you basically look back P steps, right? So P is 5, so you look back this time, 5 steps. And out of those, I want to count how many times I'm asleep. Okay, so that's basically what that is saying. And let's just make sure that we understand everything by looking at the sample input and output to make sure that, okay, I guess we actually haven't read the entire problem, the input output section yet, so let's move on. The first line of input contains 3 integers, n, which is the length of Terry's sleep pattern, P and D as described above. N is up to 86,400. And then P and D are less than, P is less than or equal to N, D is less than or equal to P. The second line of input contains a string of length N, which describes the period of time that is recorded. The ith such character is W if Terry is awake, and I at the ith second, or Z if he's asleep at the ith second. And then finally, display the integer which represents the number of seconds that Terry is tired during each of the repeating time periods. Okay, so let's see. The first sample input, you have length 2, and in the last window, the last period of 1 second, you sleep less than 1 second. So the window is actually really easy because it's the length is 1. So you just look at this. This is the entire window. So in this window, he is tired. And in this window, he has slept for 1 second. So he's not tired. So the answer is 1. This is the first one is the only time that he's tired. Okay, that's not very interesting. The next one, you have 5, okay, 5 seconds that you recorded. And in all periods of 3, you have to sleep at least 2 seconds. Okay, so this period of 3, you sleep for only 1 second, so we're tired. So this is tired. How do I do this? Maybe what I should do, I'll just draw a red arrow to indicate when you're tired. So you're tired right here, because in this window, the window of 3 seconds just before ending at this point, you did not sleep for 2 seconds. Okay. Similarly, the next window, this window of 3, you're awake for 2 seconds and only slept for 1. So again, you're going to be tired exactly at this time. And then the next one, you're also going to be tired. But why is the answer 4? Why is the answer 4? I only got 3. Anybody can tell me why is the answer 4? Because this is repeating. So even though they give you WZ, WWZ, it's actually repeating forever. So it's WZ, WWZ, and then WZ, WWZ, and WZ, WWZ, forever, both before and after. So what we have said is that this one, so if I just look at one single period, then this one, and this one, these 3 are all bad. Okay, for the reasons that I described. But what about the first 2 of these? Are they good or are they bad? We haven't even looked at them. Okay, so we haven't even looked at them, so we have to look at them. So for this one, the window is this part. So it extends before the recorded period, but when it extends before the reported period, it's just wrap around to the end. So it's like this, and you count here. So it only slept for 1 second. So again, this is also a bad spot. It's going to be tired. Okay. So then we look at the next one, this window. And this window, you look at this, there are 2 Zs here, and that means that he's not tired. So out of the 5 places, he's tired in every place except the second spot. Okay? And that's why the answer is 4. Okay, so what do we do, right? How are we going to do this? So you have a bunch of WZs in some patterns. So this is what they give you. And this can be up to 86,400. Okay, it's what they tell you. Okay, so it can be quite long. Okay, so here it is, 86,400. And then you have to worry about repeating patterns. And then you have to worry about finding how many times you slept in a particular window. So let's deal with one thing at a time. Let's deal with repeating. So repeating, basically you have something that goes around from here, and then when you go past the end, you basically come back and start again. Okay, it just goes in circle forever. And a common trick to deal with, this is a very common trick to deal with things that goes in circle when you're given only a linear list. So if this is your string, okay, and you store this, then a common trick is to actually concatenate the string with itself. So what happens? When you take this string and concatenate with itself, then you get an extra copy, like this, right? So we just take this copy and then double it. So this is a trick. Excuse me. So why is this useful? Because if I'm looking at windows starting from here, let's say in the second part of the string, I look backwards, then that's exactly the same as if I wrap around on the other side, because this part is just the end of the first string of yourself. So by doubling the string, basically, you avoid the problem. You basically turn this circular problem into a linear problem. And you only have to check, okay, so this is where you double. Then you basically only have to check the windows that ends at all these locations. Okay. So now what? So we can just say, well, if I know that they're n seconds, so this is from 0 to n minus 1, then when you double it, the index will be from n to 2n minus 1. Then I basically would loop. I would loop from n to 2n minus 1. And then for each index, I would look back p steps, right? Every time I look back p steps, and then ask how many z's are there, right? So I just look back and count the number of z's. I compare the d, and then, you know, if I compare the number of z's with d, and if it's 2 and d is too big, then I say that he's tired. But this is bad because it's actually going to be too slow. Why? Because it says that, let me make a bigger eraser here. It says that n can be up to this much, and p can be as big as n. So p can be, as it's possible that p is just as big as this. And if every spot you have to look back p steps, then your algorithm would be basically n times p, which in the worst case, it's 86,000 squared. And again, this is going to be way bigger than what you can handle because, okay, so you can just say this is about 80,000, so it's about this much square. So again, it's 64 times 10 to the 8, and that's way too much. Okay, that's 600, no, that's actually 6 billion, 6.4 billion. So this is no way, this is all very too slow. It will give you the right answer, but you'll never see it finished. So what to do? So there are actually two different strategies you can use, and I'm just going to use one. I'm just going to talk about one. So here, you can look back p steps and count how many z's there are. Okay, and so this is I, and of course this is I minus p plus 1. Okay, so you set for, maybe I should, okay, let me just actually just use a whiteboard. Okay, so I would say, so what do I do? Answer is equal to 0, so the number of times you have tired. And then I'm going to start by saying that string is equal to string plus string. So I double the string. So I have a string and I doubled it. So my string, the first part goes from 0 to n minus 1. Second part goes from n to 2n minus 1. Now I'm going to look back and see. Okay, this is a maybe, okay, let me do it this way. I'm going to compute from this location and p back. So this is n minus p is this location. That's the start and end of the window. I'm going to see how many z's there are. Okay, so I'm going to just have a int z count. It's equal to 0. And then for int I equals to n minus p, I less than n, I plus plus, if string I is equals to capital Z, then Z count plus plus. Okay, so that just counts how many Z's there are here. Now, this is a little bit strange because I'm not even interested in knowing this window. I want to know the windows that ends here, here. I want to know all the windows that ends in the second part of the string, not this one. Why am I doing this? Okay, so I'm going to tell you why. So I'm going to now start looking at all the windows, starting at this, ending at this location, so this one, and then sliding it all the way to the end. And then now, what do I do? Okay, now I have this. Let me just draw this bigger. So I know that the number of Z's here, it's in this variable Z count. Now I want to know what is the number of Z's in this window. So how can that be different? Well, basically I'm moving this window to the right by one step. So what can happen is that this new thing, this new element, may be Z or may not be Z. If it is Z, then I need to add 1 to the count. So if a string I is equals to Z, then Z count plus plus. So when I do that, basically I'm extending the window to include this one. But now I need to get rid of this. So when I move the window out of by 1, I eat up whatever is here, and then I need to get rid of this. So if string I minus P, okay, it's equals to Z, then Z count minus minus. So if there was a Z here, and I move out of this, if I move the window out of this, then I need to get rid of the count for this Z because the window no longer covers it. So what am I saying? What I'm saying is instead of going through this whole window and loop through this whole window and figure out what the number of Z's are, I realize that when I slide things over, this middle part, it's not changed. Whatever number of Z's I have here remains here. I don't have to count them again. The only thing that can be different is that I might add 1 more Z. And if this window shifted outside of it, if a Z gets shifted out of a window, then I need to remove it. And then I just say, after I've done this adjustment, if Z count it's less than D, then answer plus plus, because now I know that I'm tired. And then at the end, I just print the answer. And of course, if you look at this loop is of course linear time. And this loop, of course, it's also linear time, because in each of there are only n iterations in this loop, and each of the iteration I do 3 simple things, right? That none of them depends on n. There are no loops here. So instead of before if I was doing it brute force, I was having this complexity n times p. I actually got rid of the p. So it's actually linear time 86,000. So that's way faster, and it's going to be good enough. So again, what is the moral of the story? The first thing is when you are trying to do these circular things, you double things up, and that makes your circular problem become linear. And then the second thing is you look at how the window go from one step to the next. You're only sliding by 1 more element, and then you realize that this part It's all in common. There's nothing that you need to worry about. All you have to do is figure out what gets shifted out and what gets shifted in. And you can adjust for the count, okay, in constant time. And there's no need to redo all the different things in here because you already have them here. So that's the little trick that saves you an order of complexity. Instead of n times p, you get just n. So once again, the code is very short to write, but now you have to be a little bit more clever. Does that make sense? Anybody?
Yeah, it makes sense.
Now there's a different way of doing it. There's a different way of doing it. And I'm not going to write the code this time. Maybe I'll just erase the whole thing. And let's just pretend that I already doubled it. Okay, it doesn't really matter. So here's my this is my string. Now, what I'm going to do, I'm just going to write the indices here. So, okay, I know that this string doesn't look doubled, so let's pretend that I don't care. I just want to know how many z's are in a particular window. So what I'm going to do is I'm going to do what is called partial sum. And it's going to be an integer array. And what are the values of this array? I will count the number of the number of times I sleep from the start to this point. Okay, let me just make sure. Let me just, oops, I got it wrong. 5, 6, 6, 7, 8, 8. Okay, so what's going on? What's going on is that the number that I store here is the total number of z's from the beginning to this point. So every time, basically every time I start with 0, and then when I see a w, if I ever, oops, hang on, no, this, I made a mistake here. This should be 1. Every time I see a w, I just copy whatever is to my left. Okay, so I see a w to my left. Well, the first one is 0. W, I just copy what's on my left. I see a w, I just copy the one on my left. If I see a z, I copy the one on my left and add 1. And that will be the number of z's from the beginning of the array to this current point. Why is that useful? If I want to know, let's say this window, how many z's are there? All I have to do is I have to say, let me erase some stuff. Okay, so if I want to start, this is, let's say this is n of I, and this is I minus p plus 1, right? So if I want to know how many z's there in this window, I look at this number, partial of I. What does it tell me? It tells me that there are 4 z's. But 4 z's from where? From the beginning all the way to here, right? There are 4 z's. That's not what I want, but it's not that far because it included this part, which is what I don't want. And in this part, there was one z. So if there are 4 z's overall, but one of them I don't want, the answer is 3. 1, 2, 3. Right? So I can actually just say partial I minus p, and that will tell me that the answer, the number of z's in this interval, it's 3, right? 1, 2, 3. And it works for any interval, okay? Because you're always trying to, okay, maybe I should not say that it works for any, it works for almost any intervals. Okay, so what are the intervals? So let's try a different interval. Doesn't really matter which one I pick. So let's say this interval. Okay, so this is I, and this is I minus P plus 1. And I minus P is always just before the current interval. So how many Z's are there? 7 minus 2, which is 5. So is that right? 1, 2, 3, 4, 5. And then if you count from the beginning, of course, there's 7 of them, but 2 of them you don't count, so that's why it's 7 minus 2. The only one that doesn't work, so the only time when this doesn't work, is when I minus P plus 1 is all the way to the beginning. Because in this case, this number actually counts exactly what you want. There's nothing else to get rid of. So you have to be a little bit careful and say that only use this if I minus P is bigger than or equal to 0. Okay, so that's the only trick. And you can compute this partial sum with basically one single for loop. So it's again linear time, and then to compute the size of to compute the number of z's in a window, you can just do one single subtraction. You don't have to scan P things. So again, this is a different way of doing it. And if you really, really know your C++ well, you don't even need to write a for loop to compute partial sum, because in STL, there is a function called partial sum. And if you know how to use it, basically you can just compute a partial sum by calling the function with the appropriate parameters, and you're done. You don't even have to write the for loop if you don't want to. Okay? So that's two ways of doing this problem in linear time. Any questions? So those problems, I mean, so I don't want to say that these are easy problems. First two are easy, okay, but the third and fourth one definitely requires some more knowledge. They're not knowledge that you would normally learn in a, I don't know, 3620 and beyond, maybe. They're all things that after 2620 you should know what some of these things are, but of course, you know, it's whether you can apply them and code them correctly is a different story. So if you do 4 problems and not 5, you are going to be 37 spots to 29 spots. So you're still going to be in the top half. Remember that there's basically 73 teams, so 37 is almost the top half. And if you do it quickly, you will definitely be in the top half. Now, how much do I want this? How much more are we getting close to 9 o'clock? So let's just read this problem. This problem, let me just go and see how many people solved it. So now we're down to 29. So only about a third of the, so 71, about 71 teams solved at least one problem. And so this is, you know, definitely less than half of the teams solving this problem. And then the rest, the other ones are definitely more tricky. So let's see at least what the problem is, and then we'll say a little bit about this. Okay, so in fantasy hockey, there are N team owners, each want K hockey players. To determine which owner gets which players, the owner holds a draft. The draft proceeds as follows. The first owner select any player. Second owner can select any player except the player taken first, and so on. In general, the current owner may take any player that has not been taken previously. Once all owners have selected one player, they repeat this process until all owners have selected K players. No player may be selected by multiple teams. Okay. Initially, all players are given a ranking based on how well they played in the previous year. However, the owners may not agree with this order. So, for example, the first owner may believe that the player which was ranked third in the previous year is the best player would prefer to take him. Each owner has a preference list. On their turn, the owner selects the player that is the highest available on their own preference list. If all players on their preference list are taken, then they resort to using the ordering from the previous year. So basically, everybody has their own list, their own shopping list. They go down the shopping list looking for the first person that is not taken, take them. If the shopping list is not long enough, and they run, and everybody on the shopping list is already taken, then they just use the global ranking. Given the preference list of each owner and the rankings from the previous year, which players did each owner get? Okay, so two integers, and the number of owners, 60, K up to 1,000, which is the size of each team. The next n lines contains owner preferences in the order of the drafting. So each line starts with an integer Q, the size of the ith owner's preference list, then followed by Q names separated by spaces. In order of the ith owner's preference, no names appear more than once in the ith owner list. Next line contains a single integer P, indicating the number of players in the draft. They're up to 65,000 people. The next P lines each contain a single name. They're ordered by the previous year's ranking. Each player name is unique and comprised of at most 12 letters in English alphabet. The names in the owner's preference list are guaranteed to appear in the player list. So if somebody wants somebody in the shopping list, that person is guaranteed to be in the global list as well. Display n lines, the ith of which contains the K names of the players that were selected by the ith owner. The n team should be in the original owners, and players should be listed in the order in which they're drafted, following the rules below. So let's look at this one. So you have two owners. Each owner has to get two players. The first person wants these two players in this order. Second person wants these two in this order. And then there's 6 players available, and these are the global list. So the first owner gets Riley. No question asked. And the second person gets Shorsey. But now the first owner comes back and wants this one, but he's already gone. And his list is exhausted, so he's going down the global list. Going down the global list, this first person is gone. Jonesy is the next one, so he got Jonesy. Then the second person wants Riley, but of course that's gone too. So again, he goes to the global list. This one is gone, this one is gone, this one is gone. Finally, take this one. So that's like that. So this is a typical problem where I would say that it's in some way very simple, in the sense that it tells you exactly what you have to do, but you have to be careful and make sure that you don't miss a detail, and you have to be careful remembering everything in the right place. So it's a bookkeeping exercise. Okay, so what are you going to have? So you have a bunch of owners. Owners. Each of them has a preference list. Okay, so you have to have some data structure. So maybe the easiest thing to do is to have a vector of string. So the preference list would be a vector of string. And then you have up to 60 owners. So you have an array of vector of strings. It's a little bit complicated. So basically prefs is an array, one element for each owner. And each one of them, it's a vector of player names. Okay, so it could be, I don't know, I'll just write A, B, C, D. These are the player names that first person wants, and the second one would be maybe a shorter, maybe only B, E, and F, and whatever. Okay, so you have to read it into something like this. And then maybe each person would have kind of a head of the list. So you know where they are in the process, right? Because so there may be an array that says where they are in this list. But then there's also a global list. There's a global list that is also a vector string. Okay, there's a lot of players potentially. And then you also have to have maybe some way of deciding whether a person has been drafted or not. And you could use a set. So every time you draft it, somebody you can insert it in a set, and then you can ask in the set. You can ask using, so example, drafted dot count. So you can use dot insert if you want to insert somebody into a list of things drafted, so a player. And then if you want to know if the player is already drafted, you can ask, is this player in the set? And one way to ask for it is the count equals 1. So is the number of times this player appearing in the set 1? Okay, it's either 1 or 0. So basically what you have to do is you have to run through this K rounds. For each round, you go through each person, each of the owners. And then you just, for this person, you just walk down the list. You look at the head, wherever it is. And then you ask, has this been drafted? So you ask, has this name been drafted? If not, you draft him, you add him to the list of people drafted by person, owner 0. So again, the actual team, there'll be another vector of string array that keep track of the teams that are drafted. Okay. So you have to move, you can copy that into this vector. If it's already drafted, then you got to move head forward. And as long as the person that you look at is drafted, you keep moving forward until it's no longer drafted. And then you move it. But there's a problem. The problem is, what if everybody has been drafted and then you move head out of here? And now what do you look at? You look at nothing. And then you have to somehow go into this global list. So you have to have another head. Everybody needs to have another head that goes to the global list and figure out where they are in the global list, which is maybe kind of a pain. So it turns out that you actually don't need to worry about the global list. It's maybe sound a little bit counterintuitive. It turns out that you actually don't care about the global list separately at all. What do I mean by that? You actually just take the global list, basically whatever the global list is, you can just stick them to the end of everybody. Okay, even though the global list might also have A, B, C, D, E already. Doesn't matter. Just stick them to the end. As you walk through this list and you keep on seeing things that have been picked, eventually you'll land on something that has not been picked. And that could, even if you walk through your own list, you will end up at the global list and eventually will just find the right thing. So wow, this seems to make, I guess, the data, duplicated data, it makes your code a lot easier to write because you don't have to write one piece of code to handle your preference list and another piece of code to figure out what to do once you get to the global list. You can just stick them all into one big list for every person, and then there is no difference between global lists or local preference. Everybody has just one preference list, and you just have to write one chunk of code that handles their own preference list. You don't have to worry about what to do if you have to jump to the global list and write a separate piece of code. So this problem, I would say, it's a problem that I can imagine, I guess, giving this to a 2620 student as an assignment, and then have them struggle through and eventually get it. if they follow all the rules right? And then the main thing is you have to follow all the rules right. You have to make sure that you don't forget a detail, and you have to keep things organized. With a problem like this, there are many different moving parts. Organizing things is the main thing. Whether it's organizing things on paper, organizing things on your code, or just organize your thoughts in the head, that's very important. And that's pretty much it. Now, okay, one more thing. The way that I describe this, I keep this pointer that says where is the next one in my preference list, so that once I've gone through this, I'm not going to keep going through it over and over again, right? If I don't keep this list and I have to scan it from the beginning every step, that would be too slow. But if I keep this list, so if I keep this pointer, that means that every time my pointer will always move at least one step, and I cannot move more than whatever number of steps. The number of steps I can move is no bigger than the number of players. So if I look at the number of players is 65,000, and even if I double it, so even if I stick this preference list with this together it's only about 60, let's say 67,000. And then I have up to 60 owners. So if I multiply that together, what is it, 60, I'm doing a very rough estimate here, 7 times 10 to the 4. I just pretend that this is 70,000. That's 420 times 10 to the 4, or you can say that this is 4 times 10 to the 6, 4 million. And we said that anything under 10 million, you don't even sweat. So as long as you don't scan the list over and over again for every owner, this can be done relatively quickly. And whatever time they give you is sufficient. Okay. If you scan the list over and over again, then you're in trouble. So what time limit did they give you? Oops. 3 seconds. So that you're not even sweating at all. Okay. So it's not exactly, I guess it's not exactly number of owners times the number of so what I'm trying to say, it's not exactly a number of owners times the number of players, because every step you have to do this set. So when you do the set operations, whether you're doing insert or lookup, that's log of the size of the set, which is basically at most p, because there are at most that many players. So there's a log p factor, okay? But usually, so this is about, if this part is about 4 times 10 to the 6, and p was what, something 60, let's say call it 7 times 10 to the 4, log of that is not that much, right? So this is 70,000, log is about 16. Okay, that's about 2 to the 16. So this times this is 64 million. And now I said that things that are about tens of million, you have to be a bit careful. I said 1 to 3 seconds, and this is 3 seconds, so we're actually okay. Okay, so that's kind of the rule of thumb that I was talking about. Okay, so those are the problems I would say from this regional from last year that I wouldn't say that they're easy, but they don't require any special algorithmic knowledge. Like there's no graph algorithm, there's no dynamic programming, there's no advanced material, but you do have to be clever for some of them. Okay, and if you just do that much, you will be anywhere from 12 to 28 out of 73 teams, right? Which is not that bad. Okay, so what I want to say is that for those of you that are not trying to win this contest, what we want to do is make sure that you do the problems that are sort of the easier end, and do them quickly and do them correctly. Even if it takes you a bit longer to do, but as long as you do it correct, then you don't have to worry about penalty, right? So this, for example, these guys solved the first problem in 2 attempts in 8 minutes. So they submitted correct one in 8 minutes, but it actually counts as 28 minutes because they have an incorrect attempt. So if it takes you 10 more minutes to verify things before you submit, then you save 10 minutes for getting a wrong answer, right? Now, of course, if you're really good, then maybe you just don't have bugs to begin with, and then in 2 minutes you submit and you're done. But if you're starting out, you're probably not looking at this end. So just try to be the top third or top half, and that would be good enough. So for next week, which will be our, I guess, our last Tuesday meeting before the regional, I want to talk about the one 2 years ago now, 2018, and we will look at, again, the easier problems, right? So problem A has 63 out of 72 teams solved. Or actually, it's not how many teams out of it. I think there are fewer teams that year. Okay, why is it not showing the stat? Oh, here it is. So there are only 63 teams. So everybody solved one. Everybody solved A. Of course, B, only 2 teams solved, so you don't want to look at it. And then, you know, there are G and H, 40 teams, 2/3 of the team solved that. Same thing with H, I mean B, H index. So there are 4 problems that a lot of teams solved, and then things get a little bit harder. So if I look at the standings, 63 teams in total, 4 problems solved, I'm already in 29 spots. Oh, sorry, 31 spots. So if you solve those 4 problems, you're anywhere from 31 spots to 21 spots. So you're kind of like somewhere between the top half and top third. And if you do one more problem, if you solve one of the harder problems, then you get even higher, right? So that year we didn't do as well. Our top team was 9th, and then 13th. So I want to talk about this set, RMC 18, and look at the 4 easy problems. And then if we have time, we don't know how long it'll take to talk about 4 problems, we can look at the year before, 2017. And again, we can look at some of the easy problems that our team really didn't do so well, only solving 4 problems, but still the top half, top third of the contest, 52 teams, and there were 16. And the, you know, the easiest problem is A, and so on. I think 2016 is probably the year that we did quite well. Let me see. Yeah, we were 4th here. So, and then we solved quite a few problems. Anyway, so that's the plan. Are there any questions or comments? Let me stop.